Okay, so we're going to move on to Chapter 4, which is the propositional calculus. This is a different method of proof. We'll be building on our understanding of propositional logic, but the propositional calculus is a method of proof that's distinct from the refutation tree rule method that we've been studying so far. Okay, so today we'll learn about the nature of proof in propositional calculus, specifically the concept of direct proof. We'll learn 4 new inference rules, and then we'll do a couple of proofs in the propositional calculus. Okay, so when we talk about a deduction system or a natural deduction system, we sometimes say, what we mean is that we have a set of inference rules that we use to actually derive propositions from sets of assumptions or other propositions. So that's different than the refutation tree system, because we don't actually derive propositions in that system. We just use that to check for whether or not an argument is valid or invalid. So every derivation or proof begins with a set of assumptions, which is similar to refutation tree rules. And all successive lines of the proof are generated using inference rules, and inference rules are analogous to the rules that we use in a refutation tree system, but they're different rules. Very important to realize that this is not an extension of our refutation tree rule system. This is an entirely new system, so we'll be learning new rules. And when we do a proof, and when we arrive at or derive the proposition that we've been asked to prove, then the proof is over. So we're going to be learning first about the simplest form of proof, which we call direct proof. And here's what a direct proof would look like in an abstract way. So we're told that A, B, and C entail D, all of which these are just all stand for any proposition whatsoever. And so when we set up a proof, we set it up like this. We write A on one line, numbered 1, B on the second line, numbered 2, and C on the third line, numbered 3. And we indicate that all of these are assumptions by writing an A on the side of each one. All right, so the A's are essential. It's actually a rule in propositional calculus that you have to identify your assumptions in this way. It's like our first rule that we don't write it down anywhere. So always identify your assumptions with A's on the right-hand side. So when you finish a proof, again, abstractly, it looks like this. You've written some number of lines, which I haven't given numbers for, but 4, 5, 6, however many it takes. And then somehow on the last line, you will have derived the proposition that you were told to derive. If you do that, then you're done. And over here, you always indicate how you got each line by indicating the previous line number you were operating on and the rule that you used. Okay, so the lines of the proof are all numbered consecutively. Like the assumption lines, each consecutive line is accompanied by a rule that justifies it on the right-hand side. And the last line in a completed proof will always be the proposition you're tasked to derive from the given premises. Okay, so this stuff over here, the line number rule, doesn't really mean much to us right now, because we don't know any rules, but we will very soon. Okay, so like the truth tables and also the refutation tree rules, these rules are just going to have to be memorized. They're not hard to memorize typically. If they're going to feel fairly intuitive for the most part. They're certainly no more difficult to memorize than the refutation tree rules. But in propositional calculus, we make a distinction between basic rules and derived rules. And the basic rules are the ones we're going to be learning right off. In the derived rules, we actually prove using the basic rules. So we learn the basic rules kind of as facts, like your math facts, these are the logic facts. And then we later prove the derived rules using the basic rules. You don't have to actually accept the basic rules just as facts, though, because you can show that they're valid, either using refutation trees or truth tables. Okay, so the first rule is called conditional elimination. Conditional elimination, which we write like that. This rule, a lot of the rules that we learn have classic names from the Latin, and you might have actually heard of this one in the past. I'll just tell you right now, it's called modus ponens. Modus ponens is the name. The longer name is actually modus ponendo ponens. And so it looks like this. It says that if you have if A then B on one line and A on some other line, it doesn't have to be the next line. It can be any other line. But if you have if A then B on some line and A on another line, then you get to write B. Well, why? Because if A then B and A implies B, which you can check using refutation trees or truth tables. And so we call this conditional elimination, and we cite the lines that we're using. So for example, if this were line 5 and this were line 9, here we would write 5, 9, conditional elimination. So whenever you employ conditional elimination, you have to cite both the line on which the conditional occurs and the line on which A occurs. And this is kind of a hurdle that some people have a difficult time with. Over and over, there's always a large group of people who don't get that this rule requires you to identify both lines. And what that really means in the end is you haven't memorized the rule, and also at some fundamental level, you don't get it yet. So you really have to commit this rule to memory and make it make intuitive sense to you. Okay, the next rule is called negation elimination, and it's actually very similar to our refutation tree rule for double negation. Once again, it's not that rule. There's no overlap here at all between these two systems, but you'll see similarities at various times. So what it allows you to do is infer A from not A, like this. So if you have not A on some line, you can write A on some other line. So if this were line, say, 57 in your proof, and you might do a 57 line proof at some time, then you would write 57, comma, negation elimination. Now, there's only one line to be cited here because there's only one line that you're operating on. By the way, this rule does not allow you to go the other way. You can't go from A to not A. We'll eventually have a rule like that, but we have to derive it later. Okay, two more rules for today involving conjunction. So conjunction introduction allows you to introduce or create or construct a conjunction out of any two woofs. And because there's two, you have to cite both lines. So it says that if you have like A on line 5 and B on line 12, then you are allowed to write A and B by 5, 12, and introduction. You could also have written B and A. There's no order that's presumed here. So if you wanted to write B and A, then you would write 12, 5, and introduction. So both of those are part of the rule. And then finally, we have conjunction elimination. And conjunction elimination, which we write as and E, conjunction elimination, allows you to take a conjunction on some line and pick one of the conjuncts. So you can do it this way, A and B, A, or you could do it this way, A and B, B, right? Now there's only one line that you're operating on here, so say if this were line 7, you would just write 7 here, right? If this were line 7, you would again just write 7, comma, and identify the rule you're using. All right, so that's the 4 rules that we're going to learn today. It's important to remember that these A's and B's are part of the meta language, right? So they refer to any woof, not just atomic propositions. We've just often used atomic propositions in early examples, but you shouldn't get the wrong idea. So, for example, suppose you had these two lines in a proof, both as assumptions. You could, so this says P and Q if and only if R, then S or M. And this says P and Q if and only if R. Well, this here, and this is familiar to you, right? This is A. This here is B. And lo and behold, this here is also A, right? They match. So on line 3, you can write S or M by 1, 2, these two lines, and conditional elimination. All right, this says if A, then B. This says A, so you get to write here the B, okay? All right, so here's the review of the 4 basic rules. We've got conditional elimination, which we'll write them in this more familiar form, more compact form. So if A, then B, A yields B. Negation elimination, not A yields A, and introduction. If you have A on a line and B on a line, you can write A and B. And elimination. If you have A and B, then you could write A, or you could write B. These aren't the full statements of the rules. In the book, it actually writes it out, the rules out in English, exactly how to say them, using, as they do, phi's and psi's rather than A and B. Okay, so let's do some examples real quick. So here's our very first proof in propositional logic. Let's go ahead and prove this. P and Q, not R, entails Q and R. So there's no choices to make early on. The way you start a proof is always by writing down the assumptions like this. Okay, so P and Q, not R, are the two assumptions which we've labeled as assumptions. Don't ever forget to do that. Okay, and then what we have to realize, just say, okay, now this is a very goal-directed process. Right now, you have to say, oh, I've got to actually figure out a way to get Q and R. So this requires you to think in a way that refutation tree rules did not require you to think. And it requires you to understand kind of what the proof is, what sort of the meanings of these statements are, a little bit more than refutation tree rules required. So again, we've written it down, and we know that we need Q and R. And so now you have to sort of look at it and say, all right, how could I make Q and R? I've got to make Q and R somehow. And if you think about it a little bit, you'll see that, well, I've got an assumption, not R, which by one of my rules would create R, negation elimination, right? And also, I've got an assumption PNQ, which by one of my rules would give me Q, right? So if I had Q on a line and I had R on a line, then I could put those together by still another rule and introduction, and I would have my conclusion. So you don't always have to think this all the way through before you do it, but it really helps to spend some time thinking backwards from the conclusion, right? So you're actually reverse engineering, as we often say, the way to get to this conclusion. So on line 3, I'm doing this opposite the way I discovered it. On line 3, I'm going to write Q by 1, right? So from 1, which is P and Q, I'm going to write Q by and elimination. And elimination allows me to pull the Q out and just write it here. It doesn't require me to write the P. I could write the P if I wanted to, but I don't see any need for it. So, because P isn't over here, I don't need P in the conclusion. All right? So then I also want R. So now I'm going to write R by line 2 and negation elimination. So negation elimination, we've eliminated the negations. So, and we've written R. And then you say, oh, well, now I've got Q and R. So now I can just write Q and R by line 3 and line 4 and introduction. Okay? And that is the end of the proof because we have just derived what we were supposed to derive. Okay? That's our first proof. Let's do one more. So let's prove if P then Q and P, and if Q then S implies S and Q. So again, we're just going to write the assumptions down. It's always the first thing you're going to do. And now we're going to try to derive S and Q. So how are we going to do that? Well, again, we're going to think, how can I get S and Q? Well, that means to get S and Q, I've got to get S. Probably the way I'm going to have to do this, not always, but probably the way I'm going to have to do this is to get S on a line and then Q on a line and then put them together, construct it. That's the normal way that that occurs. So, is there any way for me to get any of these out of this? Well, you can look at assumption 2 and you could say, well, if I had Q, I could get S by conditional elimination, because Q, and if Q, then S gives me S. But I don't have Q, unfortunately. But I do have if P, then Q and P, which means by and elimination, I could write if P, then Q on a line, and I could also write P on a line. And if I had P on a line And if P then Q on a line by itself, then I would get Q. And if I could get Q, I could get S. But if I had Q on a line and S on a line, then I would be able to put them together and get S and Q. Okay, so if you didn't follow all that, it's all right. But that's the way you're going to want to start thinking. So I'm going to go ahead and write if P then Q on a line by 1, right? I got that from 1 and elimination. And now, because I want Q, and to get Q, I need P, I'm going to write P on a line. Again, by 1 and elimination. Notice that you can keep going back to the well here. There is nothing about working on a line that says that you can't work on that line anymore. And that's very different than refutation tree rules, right? Once you've operated on a line, you're done. You've dispatched it. But these are not dispatch marks. I'm just making these little marks for fun or for our amusement, but don't confuse them with being dispatch marks. There's no such thing as dispatching. So if P then Q and P, if Q then S, if P then Q, P now. Now with 3 and 4, I can get Q by conditional elimination. So if P then Q and P gave me Q. Again, check. I wrote 3, 4. Always write the numbers first. 3, 4, 3, 4, conditional elimination. If P then Q and P gives me Q. Okay? Well, excellent. Now I have Q, and that's what I wanted. I wanted Q, but I don't have S. But now look, I can get S, again, through another iteration of conditional elimination. So now it's 2, 5 conditional elimination, and I get S, right? So now I've got Q on a line, and I've got S on a line, and I remember what I want is S and Q, but now I can write that by and introduction. So that's 5, 6, and introduction. Right? And again, just check to make sure we used 5 and 6. Yes, we did. And so now we have derived S and Q. Okay? So that's the flavor of natural deduction. That's just 2 simple proofs. We'll be doing much more complex ones later. And I'll be leading you through quite a few of those too as we go. So right now, let's just review a little bit about the difference between natural deduction and refutation trees. You'll have noticed that this natural deduction feels very different than refutation tree rules, than the refutation tree system. And that's because the refutation tree system is a completely mechanical procedure. In class, I've said that a machine can do this. This is what we call a decision procedure that will determine whether an argument is valid or invalid. So what this means is that with the refutation rule system, or refutation tree system, if you just apply the rules properly, you're guaranteed to discover whether the argument's valid or invalid. Of course, you get to make prudent choices about which rules to apply, but you don't actually have to make prudent choices. You can choose randomly. As long as you are doing the rules correctly, you're going to get the answer regardless. It just might be longer, take longer, or be a bigger tree than you really needed to do. So the propositional calculus isn't like that at all. First, the propositional calculus is just a way of demonstrating that an argument is valid. That's all it does. It's not a way of demonstrating that an argument is invalid. You might want to conclude that an argument's not valid because you've tried to prove it. You've tried to derive the conclusion and you've failed. But that might not be correct. It's certainly not a proof. And you might just be wrong in concluding that. It might be that you just haven't discovered how to derive it, because some of these are quite difficult. And second, natural deduction is it's not a mechanical procedure, as we just saw. You actually have to think through this and to make intelligent choices about which rules to use. And you have to plot your way. You have to figure out a way to actually create the conclusion. You're actually making the conclusion. So, for example, it's within the rules to do this in propositional calculus. You could say we have two assumptions, if P then Q and P, and if Q then S from our previous proof. You could just start doing this. You could just start writing if P then Q over and over again by the same rule and elimination. You can just keep going like that forever. There's no rule in propositional calculus that makes you stop doing that. It doesn't slap you and say, stop that, that's stupid. It is stupid, but there isn't any rule that prevents it. And so no one would do this unless you're insane, but you might do other things that are just totally unproductive, and they're fine. I mean, they're just unproductive, but they're not against the rules. They're just not getting you anywhere. So that doesn't happen in the refutation tree system. Now, since the propositional calculus is a weaker and actually more difficult system to use, you could actually ask why we're learning it. I mean, it seems like refutation trees are just better in a certain sense. And the answer is that you can't use refutation trees forever. In more powerful languages, even in the predicate logic, although there is a refutation tree system for predicate logic, it's not a decision procedure anymore. And it's not that much better than natural deduction, maybe a little bit better. But later on, if you were to continue to study logic, you would find that there just aren't decision procedures for more complicated systems. And that's actually a very, very famous proof due to a philosopher logician named Gödel, that those decision procedures don't exist. So natural deduction is really just easier to learn at the level of propositional logic. You wouldn't want to wait until later to learn it. You want to learn how to use it with propositional logic. And then we adopt a richer language, and you already know the rules for using it, or most of them anyway. Okay, well, let's just do a little review quiz. This one is not multiple choice, so what you want to do is pause as soon as you get to a question, pause the video and figure out the answer, write it down, and then advance the video and you'll see the answer. It's only about 5 or 6 questions. Okay?